Welcome to this walkthrough of problem number 960, delete columns to make sorted 3. In this problem, we'll explore how to strategically delete columns to ensure that the remaining rows of a matrix are lexicographically sorted. Stick around as we dive into the approaches and solve this step by step. The problem requires us to process a given array of strings, where all strings have the same length. The goal is to make the rows, which are the individual strings, lexicographically sorted by deleting specific columns. Lexicographical ordering means that, for any two consecutive strings, the first string should either be smaller than or equal to the second string when compared character by character. To achieve this, we want to minimize the number of columns we delete. For example, if the input strings are already sorted, no columns need to be removed, and the result would be 0. Otherwise, we must determine the minimum columns to delete to ensure the rows are properly ordered. The output is simply an integer representing this minimum number of deletions. Let's look at the first example. We are given the input strs equals babka, basb. The output is 3, meaning we need to delete 3 columns. To achieve the desired sorting, we delete columns 0, 3, and 4. After deleting these columns, we're left with the strings ab and az, which are now lexicographically sorted. The key takeaway here is that we carefully choose columns to delete so that the remaining characters in order form a sorted sequence. Now consider the second example with input strs equals etba. The output here is 4. In this case, since there is only one row, it is not sorted, and we need to delete all columns except one to ensure sorting. By keeping only the last column, the resulting matrix becomes A, which is trivially sorted. This demonstrates that when only one row is present, we must ensure it is reduced to its smallest possible form. In the third example, the input is strs equals ghi, def, abc. The output is 3, meaning every column needs to be deleted. The rows are completely unsorted, and no columns can be preserved to make the rows lexicographically ordered. In this scenario, the resulting matrix is empty, as all columns are removed. This represents a situation where no valid subset of columns can maintain the correct order. Several edge cases can help clarify the problem further. First, if there is only one row, n equals 1, the rows are already sorted, so no columns need to be deleted, and the output is 0. Similarly, if all rows are identical, the rows are inherently sorted, and no deletions are necessary. When there is only one column, m equals 1, the rows are trivially sorted, so again, the output is 0. If the rows are already sorted in their entirety, no deletions are required. On the other hand, in the worst-case scenario, such as strs equals zyx, wvu, tsr, where no column can contribute to a sorted order, we must delete all columns, resulting in an output equal to m. These edge cases highlight the range of possibilities and help us better understand the problem constraints. To solve this problem, we first considered a brute force approach. The intuition behind this method is straightforward: generate all possible subsets of columns, delete each subset, and then check if the rows in the resulting strings remain lexicographically sorted. However, this approach is computationally expensive. Since there are m columns, the number of subsets is 2 to the power of m, and for each subset, verifying if the rows are sorted takes O and *m time. This leads to an overall time complexity of O, n times m times 2 to the power of m, which is impractical for larger inputs. Therefore, we discarded this method in favor of a more efficient solution. Instead, we turned to dynamic programming, which optimizes the process by reframing it as a longest increasing subsequence problem, or LIS. The idea here is to identify the maximum sequence of columns where the rows stay sorted, and from this, calculate the minimum number of deletions needed as m minus the LIS length. This approach significantly reduces the computational burden while still adhering to the problem constraints. The dynamic programming approach breaks the problem into manageable steps. First, we define dp, j, as the length of the longest sequence of columns ending at column j that keeps the rows lexicographically sorted. Initially, we set dp, j, equals 1 for all j, because each column on its own forms a valid sequence. Then, for each pair of columns I and j where I is less than j, we check if appending column j to the sequence ending at I maintains the lexicographical order. If it does, we update dp, j, to be the maximum of its current value or dp, I, plus 1. To determine if appending column j is valid, we ensure that for every row k, the character at strs k I is less than or equal to strs k j. Finally, the maximum value in the DP array gives us the length of the LIS, and the minimum columns to delete is simply m minus the maximum value in DP. This approach works because it reduces the problem to a well-known sequence optimization task, making it both efficient and conceptually clear. The time complexity of this solution is O(m squared asterisk n), since we compare all rows for every pair of columns, and the space complexity is O(m), which is used for the DP array. When comparing the different strategies, we see clear trade-offs. The brute force approach is conceptually simple but computationally infeasible for larger inputs due to its exponential time complexity. On the other hand, the dynamic programming approach is efficient and scalable, as it leverages the insight of the longest increasing subsequence to minimize the number of deletions. Alternative methods, such as greedy algorithms, are challenging to implement because they struggle to maintain the lexicographical order across all rows. Ultimately, the dynamic programming solution was chosen because it balances clarity, scalability, and performance. While the time complexity is quadratic in the number of columns, this is manageable given typical problem constraints, such as m being up to 1000. This makes dynamic programming the optimal choice for solving this problem effectively. Here, we are tasked with determining the minimum number of columns that need to be deleted from a grid of strings to ensure that the rows of the remaining strings are lexicographically sorted. The input is a list of strings where each string has the same length, and the output is the minimum number of columns to delete to achieve this sorting. A key observation is that the grid can be thought of as being read column-wise, meaning each column's characters must help maintain the lexicographical order of the rows. If any column disrupts this order, for instance, if a character in a column is smaller than the one directly above it, then that column must be removed. The entire problem boils down to checking each column to see if it disrupts the order and counting how many such columns exist. To solve this, we begin by iterating through each column in the grid. For each column index, we extract the characters in that column from all the strings. Once we have the column, we check whether it is sorted lexicographically by comparing the character at each row with the character in the row above it. If at any point the current character is smaller than the one above, the column is marked as unsorted. As we process the columns, we keep a counter to track the number of unsorted columns. Whenever a column disrupts the order, we increment this counter. Once all columns have been checked, the value in the counter represents the minimum number of columns that must be deleted, which becomes our final result. There are several insights that make this approach efficient. First, because each column is checked independently, we don't need to worry about interactions between columns, allowing us to treat this as a series of local checks. Additionally, as soon as we identify a column as unsorted, we can immediately mark it for deletion without performing further checks on it, which can save time. To optimize further, instead of explicitly extracting columns, comparisons can be done directly using string indexing, which reduces memory usage. The input grid is treated as a 2D matrix, and we use a simple integer variable as the counter to track unsorted columns. In terms of complexity, the time complexity is O(n*(m), where n is the number of rows and m is the number of columns, as we are checking every column across all rows. The space complexity is O(1), since we only use a counter and perform operations directly on the input without additional data structures. When applying this algorithm, there are some edge cases to consider. For example, if there is only a single row, no deletions are needed because a single row is inherently sorted. Similarly, for a single column, we only need to check if that column is already sorted. In the case of an empty grid, the output is 0 because there are no columns to delete. If all rows are identical, no deletions are required, as the rows are already lexicographically equal. Let's go through an example. Consider the input grid, CBA, DAF, GHI. For column 1, the characters are C, D, G, which are sorted. For column 2, the characters are B, H, which are not sorted because it is less than B. For column 3, the characters are F, I, which are sorted. Thus, only one column needs to be deleted. In another example, with the input ZYX, WVU, TSR, none of the columns are sorted, so all 3 columns must be deleted. These examples illustrate how the algorithm handles different cases and produces the correct result. This implementation solves LeetCode problem number 960, delete columns to make sorted 3 using a dynamic programming (DP) approach. The goal is to determine the minimum number of columns to delete to ensure that rows in the grid are lexicographically sorted. First, we initialize two variables, rows and cols, to represent the number of rows and columns in the grid. We then create a DP array DP where DP j stores the length of the longest increasing subsequence, alias, ending at column j. Initially, all elements in DP are set to 1, since each column can individually form an LIS of length 1. Next, we iterate over all pairs of columns I, j, with I less than j. For each pair, we check if column j can extend the LIS ending at column I. This involves verifying that for every row, the character in column I is less than or equal to the character in column j. If this condition is satisfied, we update DP j to be the maximum of its current value, or DP I plus 1. Finally, after computing the LIS for all columns, the minimum number of deletions is calculated as the total number of columns minus the length of the LIS, which is cols max DP. This gives the final result. The time complexity is O n asterisk m squared, where n is the number of rows and m is the number of columns. The space complexity is O m due to the DP array. Here, we begin our Java implementation by defining the min-deletion size method, which takes an array of strings as input. The first step is to determine the number of rows and columns in the input array. The variable rows represents the total number of strings, while cols corresponds to the length of each string, assuming all strings have the same length. Next, we initialize a dynamic programming array DP, where each element DP j will store the length of the longest increasing subsequence that ends at column j. We fill this array with 1 initially, since each column can at least be part of a sequence of length 1 by itself. Now, we use nested loops to iterate over all possible pairs of columns, with the outer loop iterating over j and the inner loop iterating over I, where I is always less than j. For each pair of columns, we need to check if column j can validly follow column I across all rows. This is done by iterating through each row and comparing the characters in column I and column j. If we find any row where the character in column I is greater than the character in column j, it means the sequence is not lexicographically valid, so we mark it as invalid and break out of the row checking loop. However, if the columns form a valid sequence, we update DP j to be the maximum of its current value in DP I plus 1, effectively extending the increasing subsequence ending at column I to include column j. After completing the nested loops, the next step is to calculate the longest increasing subsequence across all columns. To do this, we iterate through the DP array to find the maximum value, which represents the length of the longest increasing subsequence, or LIS. Finally, the minimum number of deletions required to make the columns sorted is calculated as the total number of columns minus the length of the LIS. This is because the LIS tells us the largest subset of columns that can remain in sorted order, so the rest of the columns must be deleted. The method then returns this result, completing our implementation. This approach ensures that we efficiently determine the minimum deletions needed while adhering to the constraints of the problem. To solve this problem, we begin by analyzing the input strs equals babka basb. The number of strings is 2, so rows equals 2, and each string has 5 columns, giving us cols equals 5. We initialize a DP array with all values set to 1, representing that each column is initially treated as its own increasing subsequence. Next, we iterate through all pairs of columns I, j, or I less than j. Starting with column 1, we compare it with column 0. For the first string, we check if the character in column 0, which is b, is less than or equal to the character in column 1, which is a. This condition fails, so column 1 cannot append to column 0, and we make no changes to the DP array. Now, we analyze column 2 by comparing it with earlier columns. First, we check column 0. In the first string, the character b in column 0 is less than or equal to b in column 2, which satisfies the condition. However, in the second string, b in column 0 is not less than or equal to a in column 2, so column 2 cannot append to column 0. There's no update to DP. Next, we compare column 2 with column 1, performing similar checks. Again, column 2 cannot append to column 1, and DP remains unchanged. Moving to column 3, we compare it with column 0. Here, both rows satisfy the condition for maintaining lexicographical order, so column 3 can append to column 0. We update dp3 to max dp3 dp0 plus 1, giving dp3 equals 2. Further comparisons with columns 1 and 2 similarly confirm that column 3 can append, so dp3 remains 2. Finally, we evaluate column 4 by comparing it with all previous columns. For each comparison, column 4 satisfies the condition to append to earlier columns. As a result, we update dp4 to 3, reflecting the longest increasing subsequence ending at column 4. At the end of our iterations, the dp array is 1, 1, 1, 2, 3. The length of the longest increasing subsequence is the maximum value in dp, which is 3. To calculate the minimum deletions required, we subtract this value from the total number of columns, resulting in calls max dp equals 5, 3 equals 2. In the second example, the input is strs equals ekba fghij. Here, rows and calls remain the same as before, and we initialize dp equals 1, 1, 1, 1, 1. When iterating through column pairs, we notice that the first string is sorted in reverse order. This means no column satisfies the condition to append to any other column because the characters are not in lexicographical order. As a result, the dp array stays unchanged with all values equal to 1. The length of the longest increasing subsequence is max dp equals 1, and the minimum deletions required are calls max dp equals 5, 1 equals 4. In the third example, we consider the input strs equals abcdf, uvwxyz. Here, rows equals 2 and calls equals 6, and the dp array is initialized as 1, 1, 1, 1, 1, 1. In this case, all columns are already sorted in lexicographical order for both strings. This means every column j can append to all previous columns, so we progressively update the dp array by setting dp j equals dp j1 plus 1. As we iterate through the columns, the dp array becomes 1, 2, 3, 4, 5, 6. The length of the longest increasing subsequence is max dp equals 6, and since all columns are part of the subsequence, the minimum deletions required are calls max dp equals 6, 6 equals 0. From these examples, we can make some key observations. The dp array is used to track the length of the longest increasing subsequence ending at each column. For a column j to append to a column I, the conditional asterisk row I equals asterisk row j for row and range rows must hold, ensuring that lexicographical order is maintained across all rows. The final result is calculated as the total number of columns minus the length of the longest increasing subsequence, or calls max dp. This represents the minimum number of columns that need to be deleted to achieve the desired ordering. The time complexity of our solution can be broken down into 3 main components. First, we have the outer loop, which iterates over all columns, running from 0 to calls 1. This contributes a straightforward O, calls, to the overall complexity. Next, for each column in the outer loop, there's an inner loop that iterates over all columns I where I is less than the current column j. This nested structure results in approximately O, calls 2, iterations for all possible column pairs, I, j. Finally, within this inner loop, we perform a character-by-character comparison for the current column pair across all rows. This comparison uses the all function, which checks rows characters, giving us an additional O, rows, for each pair. When we combine these, the total time complexity includes contributions from the outer loop, the inner loop, and the character comparisons, which we'll summarize shortly. When we merge these components, the overall time complexity of the algorithm becomes O, calls 2 asterisk rows. This reflects the combined cost of iterating over all column pairs and performing the necessary row-wise character comparisons. Now, for space complexity, the primary contributor is the dynamic programming array, or DP, which is a 1D array of size calls. This array stores the length of the longest increasing subsequence, LAS, ending at each column, contributing O, calls, to space usage. Additionally, we use a few temporary variables such as I, j, and row for the loops, which only require constant space, O1. Since no other data structures or recursive calls are involved, the total space complexity of this solution is simply O, calls. Let's analyze the algorithm's behavior under different scenarios. In the best case, all columns are already sorted across all rows. Even then, the LIS will span all columns, and the algorithm will still require calls 2 rows, due to the nested loops in character comparisons. For the average case, where columns are randomly ordered, the length of the LIS will vary, but the time complexity remains dominated by the same calls 2 rows operations. In the worst case, all columns are in descending order across rows, so the LIS computation needs to explore all possibilities, but the complexity still stays at calls 2 rows. To put this into perspective, a naive approach, which generates all possible subsets of columns and checks if each subset is sorted, would have an exponential time complexity of 2 calls rows calls. By using dynamic programming to efficiently compute the LIS, the current solution significantly reduces this to calls 2 rows, making it far more practical for large inputs. Finally, let's solidify our understanding of the mathematical reasoning behind the time complexity. The outer loop runs exactly calls times. The inner loop iterates over all column pairs, which amounts to approximately calls 1/2 iterations, asymptotically simplifying to calls 2. For each pair of columns, I, j, the algorithm performs a character-by-character comparison across all rows, which requires rows operations. Combining these, the total number of operations scales as calls 2 rows. This confirms that the time complexity of the solution is calls 2 rows. On the other hand, the space complexity remains calls, since the only additional storage comes from the DP array and a few temporary variables. This completes our analysis of the algorithm's efficiency in terms of both time and space usage. One common mistake candidates make is not checking all possible subsets of columns when using the brute force approach. It's essential to systematically explore every subset because missing even one could lead to an incomplete solution. Another issue to watch for is overlooking edge cases with duplicate rows. If the rows have identical strings, it's easy for the sorting logic to fail or produce incorrect results. Always test your algorithm against such edge cases to ensure robustness. Also, don't assume that simply sorting the rows will solve the problem. The task specifically involves deleting columns while respecting constraints, not just sorting rows outright. Additionally, inefficient string operations can severely impact performance. For example, repeatedly creating new strings after deleting columns is computationally expensive. Instead, consider optimizing by working directly with indices or Boolean arrays to track deletions. Finally, ensure you fully understand lexicographic sorting. It's based on character-by-character comparison, not numerical or custom orders. Pay close attention to handling mixed case or non-alphabetic characters correctly within this ordering system. A key insight for solving this problem is recognizing patterns in column deletions that preserve lexicographic order. If a column doesn't disrupt the order of rows, it's unnecessary to delete it. Leveraging this insight can help you move toward an optimal approach. Instead of brute forcing through all subsets, a greedy strategy can be used. This involves iterating through columns and only deleting those that violate the sorting order. Such an approach avoids the exponential complexity of brute force while maintaining correctness. Problems like this, which involve lexicographic order, often benefit from greedy algorithms, so it's important to think about minimizing operations while adhering to the constraints. However, keep in mind the trade-offs. While brute force guarantees correctness, its computational cost is significant, growing exponentially with the number of columns. Greedy algorithms, on the other hand, reduce complexity to a manageable n*m, but they require careful implementation to ensure they correctly identify which columns to delete. If you're interested in related problems, LeetCode 944 is a great starting point. It's a simpler version of this problem, where you only consider individual columns for deletion, not subsets. Similarly, LeetCode 945 focuses on making minimal incremental changes to satisfy constraints, which is another problem that emphasizes optimization. LeetCode 950, meanwhile, involves ordering constraints and uses a greedy strategy to reveal cards in increasing order. Finally, LeetCode 968 is a different type of greedy problem that focuses on placing cameras in a binary tree with minimal operations. As for alternative approaches to solving this problem, dynamic programming can be used to track the state of rows for each subset of columns. While more efficient than brute force, it's complex to implement and can require significant space, up to 2 to the power of m. Backtracking is another option, systematically exploring subsets of columns and backtracking when constraints aren't met. It's slower than greedy, but often simpler to ensure correctness. A hybrid greedy approach with early stopping is also worth considering, as it can save time when only a few deletions are needed to achieve a sorted state. Finally, let's analyze the time complexity of the different approaches. Brute force is computationally the most expensive, with a complexity of 2 to the power of m times n times m. This reflects the exponential growth from checking all subsets of columns. In contrast, the greedy approach is significantly more efficient, operating at n*m, as it avoids subset enumeration and focuses only on necessary deletions. Dynamic programming, while more optimized than brute force, still has a high complexity of 2 to the power of m*n, due to the state tracking required for subsets. Backtracking falls somewhere between brute force and greedy, with its complexity ranging from 2 to the power of m*n to n*m, depending on the specific implementation. Each approach has its trade-offs, so it's important to choose the one that balances correctness and efficiency for the given constraints. Great job following along. To summarize, we tackled the problem using a dynamic programming approach to optimize performance. Remember, understanding the problem intuitively is key to finding efficient solutions. Keep practicing, and we'll see you in the next problem walkthrough. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!